Good morning, this is your Stat Sensei, Mr. Spensei, and this is a warm up, and it says Intro to Errors, and it's actually preparing us for the error lesson. Actually, in this case, we're just going to run some hypothesis tests real quickly. So, a credit card company with more than 35,000 cardholders, that right there sounds like a population with a current mean balance of 2,500. That sounds important. That sounds like that's my population, my population mean. So it sounds like mu is 2,500. This right here sounds like my population size. The company gave free miles to a simple random sample of 36. Really good, glad they told us it's a random sample because that's a condition. And then we know our sample size here is 36. So n is 36. And found the sample mean, the X bar, to be 2,542. All right. So X bar is 2,542. Assume the population standard deviation is 109. Now, this is important. Because we have the population standard deviation, we are not working with a T. This right there tells me we are working with a Z. So our formula for our Z is Z equals X minus mu sigma divided by the square root of n. But we need to get down our important information. Well, our important information is we have a population mean of $2,500. We have a population standard deviation of $109. And we have a sample mean of $2,542. And they want to see if it has increased. So that's the important word there that says, hey, did it go up? That's why we have increased highlighted right or circled right here because of the word increased. All right, so let's go ahead. And one thing it didn't ask us to do is write down what the hypothesis is. So we should go ahead and do that before we run the test, just to make for clarification purposes. So in this case, our HO, well, that's always equal to the mean, and our mean in this case is $2,500. All right. The alternative was, did it increase? So once again, mu and $2,500, but we want to make this greater than. So we need to know that before we run their test. Now that we have that, we're going to run our test. Stat test, Z test. We don't have data, we have statistics. We have a mean of 2,500, a population standard deviation of 109, X bar of 2,542, and a sample size of 36. And I guess I should say we should have already plugged into our formula, and there it is. There's our X bar of 2542, population mean of 25, sample standard deviation 109, divided by the square root of 36. So when we do this, oops, I need to make sure I highlight a greater than. All right, and I go ahead and hit calculate. And I get a Z statistic of 2.3119 and a p-value of 0.01. All right, and they said, hey, we want to use an alpha of 0.03. So there it is, Z of 2.3119, p-value 0.0013. With that p-value, 103 is definitely less than 300. So our decision here is to reject the null. All right. So we are rejecting the claim of 2,500, and we're going to reject this, and we're going to believe that it's over 2,500. All right. Next problem. Next scenario. A nutritionist claims that the average loss for a new diet plan is 8 pounds with a standard deviation of 1.9. So this is the claim. All right. And because they're making that as a claim, we're going to say the mu is 8. And they're saying, hey, you know what? This is actually a population standard deviation of 1.9. A random sample of 35 dieters. I'm glad they told us the random sample because that's a condition, but 35 is what we're going to be needing here. That's my sample size. It looks like we have a population of 2,500 who follow the diet plan with an average weight loss of 8.7. All right. So we have a sample mean of 8.7. That's going to be really important. That's our X bar. And it says conduct a hypothesis test with an alpha equal to 1% to determine the mean weight loss is greater than 8 pounds. So in this case, our HO is, well, the mean equals 8 pounds. The alternative was it's greater than 8 pounds. And because we're working with the standard deviation of the population, this is going to be a Z. And so our Z formula, is Z equals X bar minus mu standard deviation divided by square root of N. All right, almost the same as a T, but the difference is this is a population, whereas a T will have a standard deviation. We identified our important information, population mean of 8 pounds, sample population standard deviation of 1.9 pounds, X bar of 8.7 pounds, and a sample size of 35. All right, so I've already gone ahead and plugged in 8.7 for the X bar, 8 for the mean, 1.9 for the standard deviation, and the sample size of 35. And remember, they said greater than, so we need to be looking at a greater than. So when we run it, let's see if we get these values. So we're going to go to stat test Z test. And in this case, our mean was 8. Let's slide that up just a little bit. Our mean is 8. And our standard deviation is 1.9. X bar of 8.7. And we got a sample size of 35. And we want to know if this is in fact greater than. And we end up getting a p-value of 0.0146 is what we said here. And they gave us an alpha of 1%. All right, that's going to be critical. So when we make the p-value, it's 0.0146. Well, that's greater than 100. So we're going to fail to reject a null. We can't reject it. It's 8 pounds. We cannot say that it's greater than 8 pounds, not at the alpha level 0.01. So this is what we're going to believe in this case. All right. Next scenario. A pit crew claims that its mean pit stop time for four new tires and fuel during the Daytona 500 is less than 13 seconds. All right. We have this 13-second claim. A random sample of 32 pit stops has a sample mean of 12.9 seconds and a standard deviation of 0.21. There are approximately 380 pit stops at the Daytona 500. Test a significance level of 0.05. Determine whether the pit stop time is less than 13 seconds. Now we need to be careful here. A sample mean of 12.9 and a standard deviation of 2.1. So we know our X bar is 12.9. We know our sample standard deviation, S, is 0.21. And because we're using a sample standard deviation, this is going to be a T statistic and not a Z. All right. The claim is 13 seconds, so mu is 13. All right. And we have an alpha level of 0.05. They told us the random sample. They gave us a population size. And they said, hey, we want to see if it's less. So let's go ahead, based on the less than 13 seconds, let's go ahead and write our null and alternative hypothesis. So the null hypothesis is HO. Remember, the null is always an equal. Mu equals 13 seconds. The alternative is mu, they said less, so less than 13 seconds. All right, so we know it's a t, so our t distribution is t equals x bar minus mu s divided by square root of n, and we've identified our population mean at 13 seconds. That's the claim. We got a sample of 12.9 seconds. Standard deviation of the sample, be careful, make sure the standard deviation of the sample, not population. Up here was a population, so that made it a Z. Because of this, it makes it a T. And we have a sample size of 32. So instead of a stat test Z test, we're going to go stat test T test, which is number 2. And we have a mean of 13 seconds, a sample mean of 12.9. I mean, a sample mean of 12.9 seconds, a sample standard deviation of 0.21, a sample size of 32, and we were testing based on our alternative to see if it was less. And we end up getting a p-value of negative 2.69, I mean a t-statistic of negative 2.69 with a p-value of 0.0056, and we're going to compare that to our alpha. Well, 0.0056 is less than an alpha 0.05, so our decision here is to reject a null. Well, I hope that's a good review of running a t-test and a z-test. Remember, the t-test is using the sample standard deviation. A z-test is using the population standard deviation. That's the big difference between the ones that when you use one or the other. All right, I appreciate you watching, and I look forward to seeing you on the next one. Thank you.